So I want to say a few things about the gravitational potential energy. We derived this formula, sort of, or we came up with it, and there are a couple of things. You can ask, what's its maximum value? Right. And if you look at this for a minute, you can kind of sort of realize that the smaller r gets, right, the larger, more negative this number gets. And so to get the maximum potential energy, you get farther and farther away. That makes this number less and less negative. It's going to be negative because G, M, and R are all negative. But the answer is 0. When I'm infinitely far away, I have a potential energy of 0, and everything else is negative. Any r that's less than infinity gives me a negative potential energy. And the closer I get to the surface of my planet, or whatever object I have, the more negative I get as I come in from infinity. And so the other thing I want to say is, normally, at Earth's surface, the potential energy due to gravity is just mgh, right? Where h is how far it goes above the surface. And I just want to show that this number and that number are the same for small changes in r near the surface of the Earth. And so if I calculate the change in potential energy for an object near the Earth's surface with this formula, that's just PE final. I'll drop the G minus PE initial, right? And so if I have raised an object up from some initial position on the Earth's surface at radius RE to some final position, radius of the Earth plus h, I would get this. My final position would be G minus G, mass of the Earth, say, times the mass of the object that I'm lifting, over the radius of the Earth plus h, because that's how high I lifted it. That's its final potential energy. And then its initial potential energy, if it started at the Earth, is that, right? We can rearrange this and get factor out a GMM, right? And it becomes 1 over RE, because those two negative signs cancel, minus 1 over radius of the Earth plus h. I don't know if you can see that, but that's the idea, right? And so that means my change in potential energy, let me just rewrite that again down here, G, mass of the Earth, mass of the object, times 1 over the radius of the Earth plus 1 over the radius of the Earth plus h. And this isn't plus, this is minus. Right. And if we make the approximation that h is much, much less than the radius of the Earth, this is where we can make this formula look like mgh. Okay? And so if we make this approximation, we can just do a little math on this and say, well, what is that? This is G times the mass of the Earth. I can pull a factor of RE out, and this becomes 1 minus RE over RE plus H. Right? I pulled a 1 over RE outside, and I multiplied inside by RE, and so this first term becomes 1, and then I get an RE in the numerator on this side. And then I can say, well, look, this is G times the mass of the Earth times the mass of the satellite over RE times 1 minus, I can divide the numerator and denominator by RE, and this becomes 1 over 1 plus H over the radius of the Earth. That is to say, for this fraction, I divided the top by RE, which is RE over RE, which gives me 1, and the bottom by RE. RE over RE gives me 1, and then plus H over RE. Well, this is 1 over 1 plus x, where x is a tiny number, right? X much, much less than 1. That's approximately equal to 1 minus x. And so this becomes G, mass of the Earth, mass of the object, over radius of the Earth, times 1 minus H over RE. and that gives me the 1's go away, and the minus sign makes that a plus, and that gives me G, mass of the Earth, mass of the object, over RE times H over RE, which is G, mass of the Earth, mass of the object, over RE squared times H. This piece right here, we've already said is just G, and so that's just mgh, which is what we expected to get. So this is a section on energy for satellites in circular orbits. So here's my planet, P, and I've got some satellite going around it in a circular orbit. I know it doesn't look circular, but pretend it is, at a radius r. And so that's my mass of my satellite, and it's just moving at a constant speed in a circular orbit, right? And so if I want to understand the forces acting on this, I just say the sum of the forces equals ma, and I could do the free body diagram like I've done on previous slides. And we say that the force, which is gmm over r squared, is equal to mass times the acceleration, which for a circular orbit becomes mv squared over r. And so we can look at this equation and cancel some r's, and it gives us gmm over r is equal to mv squared. Well, this looks a lot like the kinetic energy. And so we can say, look, the kinetic energy, which is 1/2 mv squared, for an object in a circular orbit, is just gmm over 2r. And so for a satellite in a circular orbit, its kinetic energy at any time is this, constant, right? As long as its r is constant. So now we can talk about the total energy. Since the total energy of a satellite is the kinetic plus the potential, we can just add them together. Here's the kinetic energy, 1/2 mv squared. And if you remember, the formula for potential energy was minus gmm over r. Well, if we use this formula for the kinetic energy, gmm over 2r, for the kinetic, and then we subtract gmm over r, what we get is the total energy is negative gmm over 2r for a satellite in a circular orbit. And I think a way to think about that is that a satellite is kind of trapped around this planet. It can't escape. And in order to escape, it's got to get up to zero energy. It's got to get to r equals infinity. And in order to do that, this would be, the absolute value of this would be how much energy you would have to add to its total energy to get it out. And so you could either put that in the form of kinetic energy or something like that and launch it with that much energy, and that would allow it to escape. When we're trying to send satellites to the moon or to Pluto or something like that, we know how much energy we need to give them. We do far more sophisticated things for those cases, but that's the idea.